Okay, so let's get started here. Number one, we have a quadratic function. They've sketched it out for us. You notice that it's concave down. That's caused by the -2. It's given to us in factorized form. Okay. Part A, we need to find the x-coordinates of the x-intercepts. These are also known as the roots. It's the points where it crosses the x-axis. Part 2 of A, we need to find the coordinates of the vertex. That's also known as the turning point. In this case, it's a maximum point. And then for part B, we're going to look at the function in the completing of the square form and find those values h and k. This is a good question concerning quadratics and analyzing them. And we're going to look at the function in three different forms, basically. The factorized, which is what they give us. We're going to look at the expanded form, or we're going to use that to get to the completing the square form. All right, so let's get started. So we have our function here, and we want to find out when the function is equal to 0. These are the roots. And since it's in factorized form, it's very handy because all we need to do is set each factor equal to 0. So we take the first factor, x minus 1. How do we make that 0? It's 0 if x equals 1. So there's our first point. It's the first root. The x coordinate is 1. All right, we do the same thing here with the second factor, x plus 3. If that's 0, then the function is equal to 0. How do we make it 0? If x is -3. There it is, the other root. Okay, so x is 1 and or x is -3. Those are the x-coordinates of the x-intercepts. All right, next up, we're going to look for the vertex. All right, there are different ways to do this. You could get the derivative and set it equal to 0, but you don't have to do that. What you could do is just say, okay, we know the parabola is symmetrical. So if we find that midpoint between -3 and 1, that's going to be the x-coordinate of the vertex. Okay, so we can take -3 plus +1, divide that by 2. That's going to give us the point in between them. It's the midpoint. And then I'm going to draw here the line of symmetry, and you'll see that it passes through the vertex there at the top of the function. Okay, so we know the x value is -1. All we have to do now is put that into the function to get the y value. All right, pretty easy calculation. Just put in -1, work it out. By the way, I hope you have paper with you and you're not just watching. Math should be done with paper and pen, really. All righty, so this is +8. So there is our vertex. -1, +8. All right. Now we're going to put the function in the completing of the square form. And I'm just going to show a little illustration here of why that is a nice form. All right. So let's take a look at how the function changes as k changes. Okay. So k is a constant, and it causes the function to shift vertically, okay, up or down. All right, so as k goes down, the function goes down. K goes back up, the function goes up. It is a just straightforward vertical shift. All right. Now the h is the horizontal shift. Okay, now notice that it's -h. Okay? So if you subtract h, this is how the graph changes as h changes. Okay? So that's why it's a nice form to get your function into. Okay? Now, it's possible, since we have the vertex, -1 and 8, that is the h value and the k value, okay? But you may not know that, so let's see how we would work it out. Okay, so there are different ways to go about completing the square. This is basically, by the way, we have to expand the brackets. Let's do that first. Okay, so expand the brackets. Just be careful that you get all 4 terms there. And then we will combine like terms. All right. And then how I like to do these is I'll take the coefficient b, which is 2 in this case. Okay. And we just divide that by 2. This is to make the square piece. Okay. And then we have to subtract that 2 over, I'm writing 2 over 2. Well, of course we know that's 1, but just to show that it's 2 divided by 2. Then you take that piece squared and you have to subtract it. Okay. So that's completing the square. The 2 over 2's we can change to 1 now, and 1 squared, it's just 1. All right, we're almost done, except that we have that -2 out front. Okay, we're going to have to multiply that through the brackets to get it into the form that they gave us. And then you're done. Okay, so remember it was minus h, minus h. So since we have x plus 1, the h must be negative. And then the k is 8. And so that is the vertex, right? And if you know that, that's good. You think you can just answer straight away. But if you don't know it, you can work it out. Alrighty, so there we go, number 1. Okay, a good way to kick things off. You should be comfortable with quadratics and be able to get them in factorized form. Expand the brackets if you need to. Get it in completing the square form. These forms are good for different reasons, okay? And you want to be able to switch back and forth to whatever form you need. Okay, that's a good way to start. And onward now to number 2. Okay, number 2. So we're given the derivative, and we're also given the coordinates of a point of the function. So you should be thinking probably integration here. Okay, so let's just take what we're given. We'll tuck that away up in the corner. All right, and then we want to have this shape of the sine curve. You should have that in your head. Okay, so on my paper, I'd probably just draw that. This is a thing you really want to go into the exam with this, knowing exactly what the sine curve looks like, as well as the cosine. All right, and I marked that orange point there, pi over 2, 1. That's going to be useful. And so we're going to integrate the derivative to get back to the function. Think of antiderivative. Okay, and the integrating the cosine is no problem. We know that the derivative of the sine is the cosine, so the antiderivative of the cosine is the sine. Okay, you want to be used to going back and forth like that. All right, and what you can always do to check yourself here is to take the derivative after you've done the integration and see if you get back to where you started. All right, so that's the function now, and so we just put in the values of the points, so we know that y is 2, when x is 3 pi over 4, and then 3 pi over 4 minus pi over 4 is pi over 2. That's why I marked that point. And what is the value? The value of sine of pi over 2 is 1. All right. So what did we do all that for? We did all that because we need to find the constant, right? When we integrate something, we have a constant that we have to add on to the function. Okay, if we have a point, then we can find the value of that constant. So that's what we're doing there. All right, so obviously C is 1. And now we have the function. So that's all. That's all we need to do here. Y in terms of x is just asking what is the function, okay? So we just needed to integrate the derivative, get us back to the function, and then we had to find the constant. If we have a specific point, then we can solve for the constant. And that's it for number 2. Now we're off to the races because the first 2 were pretty nice. We should have some marks in the bank, and then we move on with some confidence. All right, onward. Okay, number 3, we have a function f of x. It's known as a rational function, which means it has a function in the numerator and another function in the denominator. We're going to talk about the degree of those functions, and the degree is just the highest power of x. Okay, so for example, in the numerator, 2x plus 4, the highest degree of x is x to the power 1, so it's degree 1. In the denominator, we have 3 minus x. Highest power of x is x to the power 1, so this is also degree 1. Okay, so we're gonna get the equation for the vertical asymptote and the horizontal asymptote. Asymptotes are basically lines that the function approaches but doesn't touch. Okay. Then we're going to find the x-intercept, the y-intercept, and then finally we're going to draw it because we should have enough information there to draw the function. You need to have a little bit of knowledge on the general shape of these types of functions. I think that will be useful. Otherwise, let's get started. I'm going to start talking a little bit about limits. You can find these asymptotes without strictly talking about limits. I think some teachers avoid it because it's perceived as being difficult maybe. And limits are basically talking about what happens as something approaches infinity. So yeah, talking about infinity is hard for our human brains. There's no doubt about that. But it's also interesting. So I'm going to just take a minute and think about this. What does it mean for something to approach infinity? Okay, so this is how we write it. So it's the limit of the function. The limit means what does it approach as x approaches infinity. So that's positive infinity. We could also ask the question, what happens as it approaches negative infinity? That's all the way down the left side of the number line. Okay, so again, we have a hard time thinking about infinity, but we can think about what happens as it gets closer and closer to it. And this is interesting. All right, so as this function, as x approaches infinity, okay, the plus 4 in the numerator and the positive 3 in the denominator, they become less and less significant, right? Because we're adding 4 to a huge number. Okay, we're adding 3 in the denominator to a hugely negative number. Okay, so as the x gets bigger, those constants get less and less significant to the point of approaching insignificance, which means we can throw them out. They will have no significance on the limit. All right. Then we end up with that fraction, and we can divide out the x, which leaves us with -2. Okay, so that is what the function approaches as x approaches infinity. Okay, but now, like I said, it's not necessary for solving these problems to get into talks of limits. There's basically a recipe that you can follow, or you could think of it as like a program that you could give to a computer so that the computer could just spit out the answer based on certain conditions. Okay, so if you should probably, I think, go into the exam knowing this recipe. Okay, it's not too hard to remember. Okay, so basically there are three different possibilities. So if the degree, so we have the function split up into numerator and denominator, okay? And if the degree of the numerator is bigger than the degree of the denominator, HA is horizontal asymptote, okay? There is no horizontal asymptote in that case. So if you had like some x squared something, let's say quadratic over a linear, okay, that would have no horizontal asymptote. Second condition is if the degree in the numerator is less than the degree in the denominator. In that case, the horizontal asymptote is always y equals 0, or the x-axis. Okay, you can think of 1 over x, right? You might have a picture of what that looks like. Okay, this reciprocal function. Okay, it approaches the x-axis but never touches it. Okay, and then the more interesting cases are when the degrees are equal, and that is what we have in our situation, because we have degree 1 in the numerator, degree 1 in the denominator. So in that case, what we're going to do is we're going to take the leading coefficient of the numerator divided by the leading coefficient of the denominator. Okay, leading coefficient is the coefficient in front of the highest power of x. Okay. The coefficient in front of the highest power of x. Everything else can be ignored. Okay. So in our situation, we have our function here. The leading coefficient of the numerator is 2. The leading coefficient of the denominator is -1. And so this gives us the same answer that we got looking at limits. Okay, but it's a recipe that you can follow. Pretty straightforward. Like I said, you could think of giving that to a machine. If you give the order or the instructions, in clear enough language, it can perform that. So the equation is just y equals -2. All right, the vertical asymptote is actually easier, and that's when the denominator is 0. Okay, you cannot divide by 0, so the denominator cannot be 0. So that will be a line that the function can't touch that line, because at that line the denominator is 0. Okay, so it's a vertical line. It's x equals something. Okay, so we just take the denominator, we set it to 0. What x will produce 0 there? It's x equals 3. So there is the equation of the vertical asymptote and the horizontal asymptote again. All right. First part of the question done. We'll tuck that up there. Now we need to find, let's see, where y equals 0. Okay, so where it crosses the x-axis. So we just set the function to 0, right? That's y equals 0. We solve 4x. We can throw out the denominator, or you could think of multiplying both sides by the denominator. Okay, or another way to look at it is, how do we make this fraction 0? Only if the numerator is 0. Okay. So that boils down to a nice, easy linear equation. Just solve for x. We get x is -2. Okay, so that's a point that we're going to be able to plot. Where does it cross the y-axis? Or where is x 0? And that is easy. We just put 0 in for x. Okay, and we end up with 4/3. Okay, so now we have 2 points. We have the vertical asymptote, the horizontal asymptote. We should have enough now to draw this. Okay, so we'll put that over there with the other stuff we found. And let's plot it. Okay, so I'm going to draw the vertical asymptote. There, x equals 3. Okay. I'm going to draw the horizontal asymptote. Y equals -2. Okay. Now we're going to put these 2 points on. Okay. There's 1, the x-intercept. There's the y-intercept. Okay. Good. So we can think of this as 4 quadrants, okay, and the asymptotes forming the quadrants, okay. So our points are in the second quadrant there. Okay, so that piece, we know about asymptotes, so the function approaches those asymptotes but doesn't touch it, okay. Then we have another piece which is going to be sort of opposite of that, which is going to be in the fourth quadrant. And it's going to basically reflect that, okay. And so that should be good enough to get all your marks. You don't have any points in the fourth quadrant section, so as long as you get a general shape, you should be fine. Make sure you don't touch the asymptotes. I think that would be key. Okay. Anyway, this is what it will look like. You draw it. There, and it's approaching the asymptote. And then the other piece in the fourth quadrant side is similar. Doesn't touch the asymptotes. All right, so that's basically it for number 3. Okay. I think you probably need to come in with the knowledge of what these things look like. It's just sort of like you probably know what the 1/x looks like. It's essentially like that. It's shifted over a little bit. So if you get the asymptotes and you get a couple points, then you have enough to be able to draw these things. All right. On to number 4. Number 4, probability question. So we have 2 boxes, and they contain red and white balls. Part A says a box is chosen at random, so we can infer from that each box is equally likely to be chosen. So probability of choosing one box is 1/2. We need to find the probability, the overall probability that the ball is red. Part B, determine whether events A, which is box 1, is chosen, and R, that a red ball is chosen, are independent. Okay, with some intuition, we can get a good idea of what the answer is supposed to be here. Because the amount of red balls differs between the boxes, then it seems clear that the probability of choosing a red ball will be dependent on which box you choose. So if you choose box 1, it's more likely you'll get a red ball. So that would lead us to say that they're not independent. But in math, of course, we need to show some kind of a formal proof. Okay, show why that is true. All right, let's look at the boxes now. And here we have box 1 and box 2. And we said the probability of choosing either box is a half. And then let's just go over what this notation here means. Probability of choosing red given that you chose box 1. Okay, so if you have box 1, the probability of getting a red is just the number of red balls out of the total. So that's where the 5/7 comes from. And similarly with box 2. Okay, now the probability of choosing a red overall, okay, is basically going to have two branches. You could draw a probability tree here. That might be useful. You'd have a branch for each box. Okay. Let's go over the notation here. We're saying, okay, so we got two pieces which represents each branch. The first piece is the probability of choosing a red ball given that you chose box 1 times the probability of choosing box 1. Okay, so those numbers are just going to come from box 1. And similarly, the numbers for box 2. Okay, so there we have one branch, the other branch. One thing to always take note, if you get an answer, if you're doing a probability, you get something bigger than 1, you have a problem. Okay. So we're just working out these numbers. No big deal. Final probability, 9/14. All right. A little more than half, which makes sense. All right. Put that over there. Now, part B, we can show independence if we can show this. Okay. So if the probability of the intersection of events is equal to the product of each probability, then they are independent. Okay. This is how you mathematically prove independence or not. We're going to show here that we can write the intersection in this form. Okay. So the intersection of those two events, B1 and R, can be written like this: the probability of choosing red given box 1 times the probability of box 1. Okay. Conversely, they're not independent if those two sides are not equal. Okay. So we need to get those two sides, the left-hand side and the right-hand side, and just see if they're equal or not. Okay. So this is one of your equations from the book. Okay. And we can rearrange it like that. Okay. So this is how we can write the intersection. Okay. And the left-hand side, we have both those pieces. Okay. So that's for box 1. Okay. So that's the intersection. 5/14. Right. Now, all we need to do is take the probability of each and multiply them. So we take what we calculated in part A, 9/14, times the probability of box 1, a half. And what do we get? 9/28, which is not equal to 5/14. And so the intersection is not equal to the product of each probability. Therefore, they are not independent. So our intuition was proven correct, which is nice. You got to be careful of intuition. It's not always correct. Many times it will lead you to the right answer, but sometimes not. So you got to be able to do these types of formal proofs. Okay, that's all for number 4. Question 5. We have a function and we're given a tangent line at x equals 4. All right, and then a couple things that we can deduce from there, a and b. And then for part C and D, we're given a composite function h of x, which is f of g of x. And we're going to eventually find the equation of a tangent line for that function at x equals 4. All right. So first, I'm just going to draw a function just so that we can have something to look at. This is not specific to this question, but just an illustration to show what we mean by tangent lines in these things. Here's the given information. All right, and we're going to just tuck that up in the corner. All right, so here's what a tangent line looks like. Tangent line touches the function at one point. Okay. So that's an example of a tangent line. And if we're given a point, so like that, for example, we're given the x value, and then we can call the y value the value of the function at 4, so f of 4. And if you have a function, you could read it there on the y-axis. All right. So first thing we want to do is find, the value of the derivative at x equals 4. Okay, so this is kind of just the definition. The value of the derivative at any point is the gradient of the tangent line. Okay, we have the tangent line at x equals 4, so the value of the derivative is just defined basically as the gradient of the tangent, and that is 6. Okay, the tangent line is given in standard form, y equals 6x minus 1, the gradient is 6. Okay, so that's the value of the derivative. And then we need to find the value of the function at 4, and pretty simple, just take I guess I should explain why the value at the tangent line is the same as the value at the function. If you remember, the tangent line touches the function at that point, so the value of the function is going to be the same as the value of the tangent line, right? So we can just use that to get the value of the function. All right, we end up with 23. Okay, so that's just one mark apiece. Now let's move to the C part. And here we want to find the value of h when x equals 4. Okay, so let's take the definition of h. We put 4 in for x. Okay, so we have f of g of 4. We have the function g, so we can just put 4 into there. Okay, so we now evaluate that g, and we get h of 4 is equal to f of 4. We know f of 4 because we did that for part B. So there's C. All right, so far not too bad. Okay, finally now what we want to do is get the equation of the tangent of h at x equals 4. Okay, so to get an equation of a line, we basically need a point and we need a gradient. we can get the gradient with the derivative. Okay, so first thing I want to do is get the first derivative of h of x. Okay, so this is basically the chain rule. So it's the f prime of g of x times the derivative of what's inside f of x, which is g of x. So we have to multiply by g prime of x. Okay, and then we can get the derivative of g, no problem. That's an easy one to do. Get 2x minus 3. All right. We can also evaluate the derivative at 4. This is basically what the gradient is. It's the value of the derivative at 4. So we put 4 in for x. And we know g, so that's fine. And there's only one thing we know about the f prime, right? We know the value at 4. So luckily for us, we need to know the value of f prime of 4, which we have. Okay. If it was f prime of a different number, we would be stuck. We wouldn't be able to proceed because we don't know anything more about the other values. We don't know the function f, really. But luckily we know this, so we just put in 6, and there we go. There's the value of the derivative, which is the same as the gradient of the tangent. Those two things are like the same. They're the same statement. All right, now we need a point to be able to get the equation of a line. Okay, so this is the form that we're using, point and gradient. Okay, so we know that we're going to use x is 4, and we know the value of the function at 4, which we did for part C. So we have everything we need. We have our x and y value, we have our gradient, and the rest is just calculating. So I'll do everything in one step. Distributing the 30, adding the 23, and we just do the final mopping up. There you have it. The equation of the tangent line of h at x equals 4. Very nice. And there's all the 4 bits. Okay. That's it for that one. All right, number 6. Part A, we have an algebra exercise. So we're going to show that the left-hand side is equal to the right-hand side. And part B, they say hence or otherwise. This is a big clue that you're going to want to use your results from part A to help you solve part B. Okay? So go with the hence and not the otherwise. That would be my recommendation. If you take a quick look at the left-hand side of A, it looks really similar to B. Okay, the only difference is that instead of x, we have sine 2 theta. Okay, so we'll see how we do a substitution there to solve that. All right, so first part A. I'm going to show this. And the first thing you want to do is, so we're going to work on the left-hand side and basically try to turn it into the right-hand side. Okay, and if you look at the right-hand side, it's all over a common denominator, x minus 1. The left-hand side is partially has that denominator, and so the other part we want to put over x minus 1. So we can do that like so. We have a common denominator now, and we need to expand the brackets, which is no problem. Just be careful you don't miss any of those items. There should be 4, and then the minus 6. Okay, we're getting close to our target. We just combine the like terms now, and That was not too bad. Part A. Left-hand side equals right-hand side. All right, good. So now we want to use that for part B. So if we notice the similarities of the left-hand side with part B, if we just change the x for sine 2 theta, okay, we can do a substitution here. And so just think of sine 2 theta as a variable. That is a thing that's unknown. So it's an unknown thing, just like x is an unknown thing. It just has a longer name, but it can be treated as a variable, just like x is a variable, y is a variable, sine 2 theta is a variable. So just think of that as one thing. Okay. So using part A, we can rewrite this as the right-hand side was. Okay. All right. This now makes it a lot easier to solve. Okay. First thing I'm going to do is factorize the numerator. Okay. So this shouldn't be too bad. It's a non-calculator test, remember, so they're going to make things that are relatively, easy or possible at least to solve. Okay. So to factorize this, okay, the only way to make 2 sine squared theta is with 2 sine and then that 1 there. Okay. And then there's not a lot of combinations here to try. So I think you'll be able to find that. Okay, so there's the factorized numerator. All right. Now, how do we make this 0? The only way to make it 0 is if the numerator is 0. So we can just look at the numerator. We can throw out the denominator. So we have this now. And then to make this 0, we just look at each factor. Okay. So if the first factor is 0, then it's 0. So we just solve this now. We're going to solve for 2 theta. All right, so you subtract 1, divide by 2. So sine 2 theta is negative 1/2. Good. Let's look at the second factor. Sine 2 theta minus 3 is 0. Add 3 to both sides. Now we see that we have sine 2 theta equal 3, but sine 2 theta, the maximum value of that is 1. This is another place where it's good to have that picture of the sine curve. Okay, sine curve has a maximum of 1, minimum of negative 1, so it can't be 3. So we can throw that out. And now we just deal with our first solution. Okay, so we're going to have to look at the quadrants here now. Okay, so when is the sign negative? It's in, let's see, ASTC, so quadrant 3 and 4, where it's negative. Okay, let's first look at the range here. So for theta, they told us that it should be between 0 and pi. And so now you might think like, oh, that's only the first and second quadrant, so I'm not even going to get to the second or to the third and fourth quadrant. Okay, but remember now we're dealing with 2 theta. Okay, so to look at the range, we could just double that, right? Multiply everything by 2. Now I've got my 2 theta. That's what I'm working with. And so the range of 2 theta can be from 0 to 2 pi. And so that does include all 4 quadrants. All right. So we'll solve for 2 theta, and then finally we'll get theta. All right, so how do we get negative 1/2 for the sine? Let's look at the unit circle here. All right, and go all the way to there. We're in the third quadrant, and we got a triangle we want to look at. So let's pull it out, take a look at it. Okay, this is a famous triangle. Hopefully you've got this in your head. Okay, also known as the 30, 60, 90, but we're using radians here, so that's what it looks like in radians. Okay, and so you notice that the sine in that triangle is negative 1/2 over 1. So the sine of that angle is negative 1/2. All right. That's good. Slide it back in. We need to look at the fourth quadrant. Okay, first let's solve this. Okay, so how do we get there? We go pi, and then we go that much more, so pi over 6. Okay, so that angle, okay, starting at 0, we go all the way to pi, and then we add pi over 6. That gives us 7 over 6, and then to get theta, we divide by 2. All right. Fourth quadrant triangle is similar triangle, so I'm not going to pull it out. I'm just going to show how we get there. We're counting from 0 to there. All right. The easiest way to think about that is that it's 2 pi, so it's pi over 6 short of a full circle. In other words, 2 pi minus pi over 6. Okay, that will give us 2 theta, and then theta we divide by 2, we get 11 pi over 12. And that's all. That's all for that one, solved. Okay, so when you see hence, go with the hence, don't go with the otherwise. Okay, it's a big clue that what you've already accomplished you can use. And it's usually, I would say that if they didn't tell you, or if they didn't give you the A part, it would be really hard to come up with that. So you can think of it as like they're trying to help you a little bit. Okay. All right. Okay. Onward. Okay. Question 7. So we have a particle moving along the x-axis, and we're given a function for the velocity, and it's in terms of t. Okay. So we're going to have t on our x-axis, and then in this case, velocity would be the y-axis. Okay. So part A, find the value of t when p reaches maximum velocity. So you should be thinking derivative, right? That's how we find max and mins. A2, show that the distance is equal to this, 88 over 27. Okay, so we'll have to get an expression for the distance to be able to do that. B, we're going to sketch the velocity, and C, we'll find the total distance traveled by p, which is going to be the area under the velocity graph. Okay, so here's the velocity. That's given. We're going to take the derivative to find the maximum. It's a pretty straightforward derivative to find. And we're going to set it to 0. Okay. Let's move the 6t over to the left. Okay. Easy stuff here. Divide by 6. Simplify that to 2/3. So when t is 2/3, the velocity is maximum. All right, put that there for future use. Okay, now we need an expression for the distance traveled, sometimes called displacement. Typically we use S sub t. S sub t. Okay. And how do we get that? Well, remember that the velocity is the derivative of the distance function. And so if we integrate the velocity, we get back to the distance. Okay. So we'll take our velocity and integrate that. Pretty straightforward again, just the opposite of the power rules there. And then you have a constant at the end. All right. And so to get this, the the final expression for the distance, we need to solve for c. Okay, so we put 0 in for t. So all those pieces with t are zeroed out. We're left with only c. We also know that the distance traveled at when time is 0, so at the initial time, we're told that the particle starts at the origin, so its position is at 0. Okay, so the distance is 0, and that means that c is 0. Okay, so now we have a final expression for the distance. Looks like that. Then for the second part of A, we need to just calculate this when t is 2/3. All right, pretty straightforward. Check my numbers, please. I hope they're right. Okay, now we need a common denominator, which would be 27. Multiply the first one by 9, second one by 3. All right, we're everything over 27 now, and then we just add it up. 96 minus 8 there. So 88 over 27. That's always nice when you match the number. I like those questions when they give you the answer and then you match it. That's nice. All right. Now, to sketch this, we want to find where it crosses the axes, right? Okay, so the first one we can do is set t to 0, okay? So this is when we cross we'll call it the y-axis, the vertical axis, let's call it the vertical axis. Okay, so it crosses there when t is 0. So you just put 0 in. What's left is 4, so you have a point there. That's going to be one of the points that we can plot to help us draw this graph, 0, 4. All right, now we want to find out what is the t when the velocity is 0. Okay, so this is a quadratic. We could have potentially two answers, right? So let's, first thing I want to do is just rearrange it a little bit. So I've got it in descending order. Okay, no problem. I'm going to multiply by -1 so that I can get rid of that -3t squared. I'd rather have that positive. So I can do this, I'm allowed. I can multiply both sides by whatever, anything I want. -1 does the job of switching all the signs. That's what it does, like a switch. All right, so all those are switched. Now we're in a non-calculator paper, right? Should expect this to be factorizable. So we know we have a 3t and a t. That's the only way to make 3t squared. And then not a lot of combinations to check. You can pretty quickly come up with that, I think. So that's the factorized form. Okay. Because it's a non-calculator test, we wouldn't expect, I don't think you'd expect to get a decimal answer there. All right. So anyway, we have our answers now. When we solve those two factors, we set them to 0, basically. Okay, the first one is 0 if t is 2/3. No, sorry, -2/3. Second one is 0 if t is 2. And we can throw out the negative because we are only looking at positive time. I think that makes sense. What would negative time be? Going back in time? We're starting at the origin. We're starting at t equals 0. Okay, so we're only going to look at the positive. This is one of the roots where it crosses the horizontal axis. So t is 2. The value of the velocity there is 0. Okay, so I got two points that we can plot. All right. We also have the maximum point. Now, it doesn't say that you have to plot this, but you already have this t equals 2/3, right? So you know that's the maximum. And if you drew something wildly different, then you could lose marks, I'm thinking. Okay. So if you show the maximum at another place rather than 2/3, you're kind of showing that you don't understand that maximum. So I would just plot that. I don't think you have to be too worried, but you should show that at 2/3, which is, you can estimate that 2/3 from 0. And then it should be the turning point. The other 2 points, we can definitely plot them nicely. Okay, there's 0, 4. There's 2, 0. Okay, we have enough now to draw this. All right, so it's a parabola. We're only looking at positive t's, and we stop at 3, I think. Yeah. Okay. So for the final part, to get the distance, you can get the distance by integrating the velocity. Okay, so I actually talked about that earlier in the question. Okay, so the distance can be gotten by finding the area under the curve. All right, now one thing we have to recognize here is that from 2 to 3, the area is below the t-axis, I guess we'll call it the t-axis. Okay, so you're going to get a negative area or a negative distance. Okay, and what we need is the total distance. So we need to think of this as like the absolute value. So there are a couple different ways you could do it. But essentially, you're going to have to break this into 2 different integrals and then add them together. So you can take the absolute value of a2 and just add that. Or knowing that it's going to be a negative, you could subtract it. So you'd be subtracting a negative, which would be a positive. Okay. So let's look at the integration here. Okay, so the way I'm writing it here is distance is a1, so that's clear, plus the absolute value of a2. So that absolute value is going to switch the negative to a positive. So we just have 2 pieces we have to get. Piece number 1. So remember, we're integrating the velocity function, which we already did. So you have that work already. You can just put it in and evaluate it now at 2 minus the value at 0. All right, pretty easy numbers. Got all those 8s, all zeros when it's 0, right? Because you got t is 0. So I got a positive 8 and negative 8. They're going to cancel. You're left with 8. Okay, so that's one piece. A1 is 8. A2, same function, just different limits. So from 2 to 3. So same function. Now we put 3 in for t and subtract 2 in for t. We already did that work for t equal 2, so we know that's 8. You don't have to redo it. We put 3 in. Again, nice, easy numbers. And we get what? 3 minus 8 is negative 5. Okay. So as we expected, it's a negative number because it's below the t-axis. And because we want total distance, we take the absolute value and switch that to a positive. And that's it. 8 plus 5, 13. There you have it. All right, so looking at how these things, derivatives and integration, are related and how they can solve these types of kinetic type problems. All right, onward. Okay, number 8. Questions here starting to get bigger, 15 marks. Here we have an exponential function, a to the x, and we're given a point, and we need to show that a equals 8. Okay, so we'll be using some logarithms, no doubt, and exponential function knowledge. Okay. I'm going to find the inverse. Okay. Should be no problem. Only 1 mark. Then we evaluate it at square root of 32. Okay. And then the big part, D. You have an arithmetic sequence like that. All right. And we have to do some analysis of that. All right. Looks good. Okay, so point that we're given is there. 2/3 and 4. There's the function. Okay, so we're just going to put 2/3 in for x. We know the answer. It's 4. Solve for a. Okay, so I want to get rid of that power 2/3, so we can get rid of that by raising to the power 3/2, because they're going to multiply together. It's the reciprocal, right? Multiply them together, you're going to get 1. So we have a to the power 1. Okay, and then we just need to simplify this 4 to the 3/2. So we can split it up like this. 4 to the 1/2 to that raised to the power 3. 4 to the 1/2 is just square root of 4. So it's 2 to the power 3 equals 8. Okay. Not a big deal. Okay. Got to be good with your rules of indices. Okay, obviously. As long as you're good with that, that's a pretty nice one. Okay. Now we need to find the inverse, and so normal practice is you just switch the x and the y, and then we make y the subject. Okay, so if we use log base 8, okay, if we use log base 8, then the 8 is going to more or less disappear, as we will see. Okay, so I take log base 8 of both sides. Okay, still equal, obviously, because I just did the same thing to both sides. And then we'll use this log rule. We can pull the y out front. Okay, there, and so log base 8 of 8, that's essentially like asking the question, 8 to what power makes 8, right? What is the exponent that makes 8? And that's obviously 1. So we can throw that out, and there we have the inverse. Okay. Fine. Now we're going to evaluate it at square root of 32. So just put that in. I'm going to change the square root to power 1/2. Easier for me to work with that. And this is just the process of simplifying this thing, 32. 32 should be a pretty well-known number. These base 2 numbers should know. Okay, first of all, we're going to use the rule where we can take the index out front, so that we have 1/2 out front now. Log 8, 32. Let's rewrite the 32 as 2 to the power 5. And we pull the 5 out front. All right. Now we ask ourselves, 8 to what power makes a half? Okay. We know that cube root of 8 is 2, right? So that's power 1/3. So that thing is equal to 1/3. And that's it. That's the value of the inverse at square root of 32. All right, now we get into the meat of this question, where we have first, well, let's see. Okay. So we have an arithmetic progression, right? They all have a common difference. That's the definition of an arithmetic progression. So the common difference we'll call D. And we can set up equations here. You can take the difference of any subsequent terms. So here I'll take the second term minus the first term. That equals D. All right. I'm going to use log rule for subtraction. Then I'm going to write this in exponential form. Okay? So you want to be good at moving back and forth between log functions and exponential functions. Okay? So what I'm doing here is I take the base, I put it up front. The power is D, and the answer is P over 27. Okay, let's move that sequence down there. Okay. So what do we have now? Okay, we can, because the difference between each subsequent term is the same, we can go through that process for all of these. The third minus the second, you're going to get this ratio. Okay. You could do it for the fourth minus the third. You'll get that ratio. Okay. So we're showing that the ratio between subsequent terms, so in other words, the second term divided by the first, or the third term divided by the second, fourth term divided by the third, these are all equal to 8 to the power D. And that is the definition of a geometric sequence, right? It has a common ratio. So it is a geometric sequence, which is what we're asked to show, and the common ratio is 8 to the power D. Okay. Now we can find this common ratio by taking the fourth and the first terms. These are known terms. In the middle we have P and Q, which are unknown, we're trying to find. So let's take the fourth and the first. Fourth and the first. If we divide those, we get the ratio to the power 3, right? So to get from the first to the fourth, we have to multiply by the common ratio 3 times. Okay. So we can solve this. Those are nice numbers because they're powers of 3, right? So it's really important, I think, to have common knowledge of certain numbers. When you see 125, you really want to automatically say, I know that's 5 to the power 3. That could be useful. Not always, but if you know that it equals that and you can use it in place, then it will definitely help you. Same with 27. It's good to recognize immediately that that's 3 to the power 3. Okay. And because we've got all power 3s here now, you can simplify this nicely and get the common ratio. It's 5 over 3. All right. Now to get P, we can take the first term and multiply by the common ratio. This is how you get from one to the next, right? So this is no problem. We get 9 times 5 is 45. Then we can get Q, because Q is the next term. So we take P, multiply by the common ratio. what do we get? 15 times 5. So we'll have q equals 75. And there you have it. Okay. Combining knowledge about arithmetic sequences, geometric sequences, and logarithms and exponents and all sorts of good stuff. All right. That was a nice one. Okay. On to the last one. Okay. Finally to number 9. All right. So first, they're showing us a function here, right? And we got to be careful because this is the derivative. And we need to take a little time to get our head around this because we're used to looking at functions, right? And then getting the derivative from there. In this case, we have the derivative, and we're going to be thinking about the function, which is where the derivative came from, okay? So try to keep that in the forefront here. This is the derivative. We're looking at the derivative. Okay? We're going to have to answer some questions about the function, which is where this came from. Okay. And what we'll do is we'll see how the derivative gives us information about the function. Okay. So for A, we'll find the values of where f is increasing. So that's the function. Now, you got to really keep this in mind. That is not what we're looking at. We're not looking at the function. We are looking at the derivative. And we're going to have to answer questions about the function. So the function is kind of like it's in the dark, right? It produced this derivative, but we can't see it. We don't know what it looks like. Okay. Part B. Okay, another question about the function, the local maximum. So all these things are questions basically about the function. C is local minimum and points of inflection. And then D, finally, we have to interpret what this means of total area enclosed by the graph of the derivative. Okay, so that's D. All right, so let's take a look. Okay, so here's basically what the derivative looks like. Okay, remember, it's not the function, it's the derivative. Okay, and here are all the important points. Okay, all right. So a couple things. Let's just point out here. Turning points. What does the turning point mean? A turning point is when the first derivative equals 0. Okay? First derivative equals 0, and the direction of the function is changing. So turning point, as far as looking at the derivative, is like point P here. Okay? So the derivative is 0. Okay? So it's either a max or a min, or it could be a point of inflection. If the derivative is passing from negative to positive, which it is here, then it's a turning point. Another turning point when x is 0, okay? So the derivative is 0, and the derivative is going from positive to negative, right? So that means turning point. Okay. So first part, where is the function increasing? Okay. And this is found from the derivative. Okay. The derivative tells us exactly this. The derivative, when the derivative is positive, it means that the function, where it came from, is increasing. Okay. So that section from P to 0, the function's increasing. Okay, so I'm marking all the positive parts, so everything above the x-axis in green, everything below the x-axis in red. Okay. So when the derivative is greater than 0, the derivative is greater than 0 when x is between p and 0. So this is where the function is increasing. Okay, that's part A. Okay. A local maximum of the function, okay? So it's where the derivative is 0, okay? And it's where the derivative, okay, let's think of the function now. A maximum is where it's increasing, okay? The derivative is 0, then it starts decreasing. So the derivative goes from positive to negative. Where does that happen? Okay. It goes from positive to negative at point 0. Okay. So at 0, the derivative is 0, and it's passing from positive to negative, which means the function is increasing and then hits 0 and then decreasing. Again, we've got to get our heads around this idea that we are looking at the derivative, not the function. We need to try to picture where this derivative came from. Okay, where do we have a local minimum? So a local minimum would be the function is decreasing, goes to 0, and starts increasing. Okay, that's at point P now. Okay, because the derivative is negative, then hits 0, then switches to positive. Okay, that means the function's going down, and then turns around at P, starts going back up. So it's a local minimum. Okay, inflection points now are other points where the second derivative is 0. Okay, so the second derivative, which is the derivative of this graph that we're looking at. Okay, so when is the derivative of this equal to 0? It's at these points Q, R, and T. Okay, you can see that the if you drew a tangent there, the gradient would be 0, right? It'd be horizontal. Okay, so these are all points where the second derivative is 0, and these are points of inflection. Okay, so the gradient of the first derivative is 0. Okay, I admit this can get confusing. Just keep in mind, we are looking at the first derivative. Okay, the second derivative is the derivative of that. Okay, so the second derivative would be 0 there. Would also be 0 here, right? Just remember, you can draw a tangent line that would be horizontal, right? That means the second derivative is 0. Okay, also at T. Okay, so those 3 points are points of inflection. All right, no problem. Now, what do we need to do? All right, so now let's see. We're given some information. We're told that the total area here is equal to 20. Okay, total area. Now the total area, again, this is similar to the previous question. Some of the area is below the x-axis, which is negative. Okay. The total area, I have to assume that they mean the absolute value of the area. Okay. So we're told that that's 20. So we could take the absolute value of the second piece, or we could just subtract it. Well, let's see. How am I going to do this? Okay, so it's the absolute value of the derivative. Okay. So it would be that first area minus the second area, because the second area is a negative, and if I subtract that, it's like adding it. So it will make both of those areas positive. All right, and all we need to do is know that when you integrate the derivative, you get back to the function. Okay. So the integral of the derivative is the function. So we just put the limits in. So the first piece we put in 0 and p. We subtract the next piece where we put in t and 0. We're also given some information about f of p and f of t. Okay, so let's just simplify this. Okay, we'll combine the f of zeros. So we got two of those. And then I'll put minus outside, put those in brackets because we know actually this piece, right? We know f of p and plus f of t is 4. And we know the area. So we have everything. We have enough now to solve for f of 0. So we got 20 there, 4 there. Then we just solve for f of 0. Add 4. Divide by 2. Finito, guys. That's it. All right. I find that this question takes a little bit of you got to get your head around the idea of looking at the derivative rather than the function. So you think about where it came from and what it tells you. And yeah, a lot of marks there to get. So that's all for now. Good luck on your studies. And I hope to produce some more of these. So keep your eye out.